Hello, grade 10. Welcome. The purpose of this video is to go through the most recent dimensional analysis check for understanding, to review all of the must-have skills that you have for this unit and a few of the amazing skills. So I'm going to go ahead, jump in here, go through each question. Make sure to pause the video as necessary and watch for understanding. You should be asking yourself, could I do a problem like this completely independently? If not, pause the video, figure out what's going on, watch again, ask questions until you reach a point of being able to do this independently. All right, so our first problem here is we have a chemical reaction represented in words, and we have to translate that reaction into symbols. So I'm going to go ahead and read my reaction. I see solid strontium sulfide and hydrochloric acid, and they give me the formula for hydrochloric acid dissolved in water, yield hydrogen sulfide gas, and strontium chloride dissolved in water. All right, so my highlighting here is really intentional. I'm noticing that I have my reactants separated using the word yield and my products. I see I have two different reactant molecules. Reactants or products are separated with and two product molecules also separated with and. So let's dive in and figure out what each of these compounds are. So, solid strontium sulfide. Well, strontium sulfide, I'm going to find those in the periodic table. Let me do this in a way that is a little bit easier. All right, so strontium sulfide, I see I have a metal and a non-metal. So I'm going to have an ionic compound here. Strontium is in the second column, so when it forms an ion, well, strontium has two valence electrons because it's in that second column in the periodic table. So the options for forming an ion are losing two valence electrons or gaining 6 valence electrons. If you're not feeling comfortable in that, go back to Unit 1. That was the entire focus of Unit 1. Strontium, again, could lose 2 valence electrons or gain 6 valence electrons to get to a full shell. It's easier to lose 2 valence electrons. When I lose 2 negative things, I get a charge of 2+. Sulfur is way over here, a nonmetal with 6 valence electrons because 1, 2, 3, 4, 5, 6, it's in the 6th column. All right, so it could either lose all 6 valence electrons or gain 2 to get to a full shell. Easier to gain 2 valence electrons, and when I gain 2 negative things, my charge is 2-. All right, so to form a neutral compound, well, Sr2+ and S2-, I only need one of each, so I end up with SRS. I know it's solid, so I'm going to put solid after the compound symbol. And I represent with a plus. Hydrochloric acid, they give me. Dissolved in water, I represent as aqueous, AQ. Yield, I represent with an arrow. Hydrogen sulfide gas. Well, hydrogen sulfide, I have a nonmetal and a nonmetal. A nonmetal and a nonmetal make a covalent compound. So let's see what this covalent compound might look like. I have sulfur again. I'll go ahead and draw the Bohr diagram for sulfur so I can see how it's going to form a covalent compound. Sulfur is number 16 on the periodic table. So when it's neutral, it will also have 16 total electrons. So I've shown 10 electrons, and I'm going to show 6 more. 6 valence electrons make sense to me because I'm in the 6th column. All right, so sulfur is trying to reach its lowest energy state with 8 valence electrons. Hydrogen, when it's neutral, has only 1 electron because it has 1 proton. So, let me back up a second. So, hydrogen and sulfur. I know hydrogen and sulfur will be in my compound because it's called hydrogen sulfide. Hydrogen and sulfur, one hydrogen atom and one sulfur atom are going to share 2 electrons. Hydrogen now has 2 electrons, which completes the first energy level. So hydrogen is at its lowest energy state. And sulfur has 1, 2, 3, 4, 5, 6, 7. Not quite there yet, not quite to that magic number of 8. And so sulfur is going to need a second hydrogen atom in order to be full and reach its lowest energy state. So hydrogen sulfide, I'm going to require 2 hydrogens for every sulfur because I need all of the atoms to be at their lowest energy state. And so let me just make this a little bit smaller. Oops, I just wanted to make the Bohr diagrams a little smaller to give myself some more space. And okay, we'll just leave it like this. Hydrogen sulfide. And I see that it's a gas, so I'm going to put G for gas. And then finally, strontium chloride. Strontium chloride. Well, I have a metal and a non-metal, so ionic, so I need to form ions again. Strontium still forms an SR2 plus ion. That's the ion that strontium tends to form because it has 2 valence electrons. Chlorine is way over here. It's a halogen in group 17. 7 valence electrons. It can either gain 1 valence electron or lose all 7. When I gain 1 valence electron, I have a charge of -1. That's the most likely ion for chlorine to form. So SR2 plus, Cl minus, in order to form a compound, I'm going to need 2 Cl minuses to form a neutral compound. So I will have SrCl2 dissolved in water is aqueous. All right, so here is my reaction. This is combining what we learned in Unit 1 with forming molecules and compounds with what we're doing in Unit 2, which is chemical changes. I now need to balance my reaction. There are several videos on balancing reactions, so I'm going to go through this fairly quickly because you have 3 different video resources you can use for balancing chemical reactions. All right, set up my atom inventory. S, H, Cl, Sr, S, H, Cl. I'm starting with 1 of all of these. 1, 1, 2, 2. And I see that if I just add a coefficient of 2 in front of my HCl, I am balanced. All right, so I then need to show the diagram. Remember that ionic compounds, I show the ions that form, the charged particles that form. Covalent compounds, I connect my atoms. I do indeed have neutral atoms because it's a covalent compound with lines. So SRS, this was ionic, and the 2 ions are SR2 plus, S2 minus. So that's my diagram for SRS. Not my symbols. SRS is the symbol. The diagram shows my ions. All right. HCl, this was a nonmetal and nonmetal. It makes a covalent compound. And I need 2 of them to be balanced. So I'm going to show 2 HCl's. H2S, S, H, H, H2S. It looks kind of like H2O, but with an S instead. And then SrCl2, this was another ionic compound. So I'm going to show my ions. You can put circles around the ions if that helps you distinguish where the ions are. All right, so there you go, representing reactions in our 3 ways: words, symbols, and diagrams, as well as balancing the reaction. All right, we now have a couple mole questions. This is going to deal with one of our mole must-haves, and question 2 deals with the other mole must-have standard that we're working with. All right, so I'm given this chemical reaction. If I start with 8 moles of aluminum, how many moles of aluminum oxide are produced? So my starting unit is moles of aluminum. My final unit is moles of aluminum oxide. I look at my reaction. I didn't even have to figure out aluminum oxide. It's a metal and a non-metal, so it makes an ionic bond. I could have formed the ions and gone to Al2O3, but I didn't even have to. They gave it to me, so moles of Al2O3. Now, my conversion factor to go from moles of one reactant or product to moles of another reactant or product is the coefficients. All right, so I know for every 4 moles of aluminum, I have 2 moles of aluminum oxide. Coefficients convert between moles of one reactant or product to moles of another reactant or product. All right, so let's go ahead and set this up. I have 8 moles of aluminum times, if moles of aluminum are here, that same unit needs to go on the bottom in my next conversion factor, moles of aluminum. And on top, I need my final unit, moles of aluminum oxide. And I know 4 moles of aluminum, so I'm going to put a 4 next to the aluminum. Gives me 2 moles of aluminum oxide. And so I now have 8 times 2 over 4, which is equal to 4 moles of Al2O3. So this is our first required conversion factor, is looking at coefficients as a molar ratio. All right, question 2, my second required conversion factor, my second must-have. How many aluminum atoms are present in 8 moles of aluminum? My starting unit is moles of aluminum. My final unit is equal to aluminum atoms, individual atoms. So here I'm using this giant number to count, and here I want the actual number of atoms. All right, so my conversion factor is 6.02 times 10 to the 23rd atoms of aluminum, or any object really, over 1 mole of aluminum atoms, or 1 mole of anything gives me 6.02 times 10 to the 23rd individual things. So 8 moles of aluminum times, if moles of aluminum are here, then in the bottom in my next conversion factor, I need moles of aluminum. I'm trying to get into aluminum atoms, just single atoms. In 1 mole of aluminum, I have 6.02 times 10 to the 23rd aluminum atoms equals, and I'm going to need to put this into my calculator. So in my calculator, 6.02 second E23 times 8 gives me 4.816 E24, 4.816 E24, and 4.816 E24, which I write as times 10 to the power of 24 aluminum atoms. I don't put the E from my calculator into my answer. I write it in scientific notation. All right, so that gets through our must-haves. Let's look at our 2 amazings. So, how many moles of hydrogen atoms are present in 3.5 moles of water molecules? My starting unit is moles of H2O. My final unit is moles of just H. Notice, unlike here, I don't have a chemical reaction. I don't have a chemical reaction, I just have a single compound. My conversion factor is, well, for every 1 mole of H2O, I actually have 2 moles of individual H atoms. Just like if I had a dozen water molecules, I would have 2 dozen hydrogen atoms because each individual molecule has 2 hydrogen atoms. Well, if instead of a dozen, instead of 12, if I have a whole mole's worth, 6.02 times 10 to the 23rd, then I'd have 2 moles of hydrogen atoms. All right, so the first amazing conversion factor is that subscripts also serve as molar ratios for an atom or ion to an entire compound. So I can use subscripts as a conversion factor if I'm trying to convert between part of a compound and the whole compound. All right, so for 3.5 moles of H2O, I have 1 mole of H2O, moles of H2O, moles of H2O. This is going to cancel. And 2 moles of H atoms. And so I get 3.5 times 2 divided by 1, 7 moles of H atoms. All right, finally, the second conversion factor that's an amazing is molar mass, which is using these masses that we find in the periodic table. So in order to find the molar mass, let me do my starting unit, final unit. And the conversion factor when I'm dealing with mass is indeed molar mass. So the question, what is the mass in grams of 2.45 moles of silicon dioxide? Starting unit, moles of SiO2. Final unit, mass of SiO2. Conversion factor, molar mass. So let's look at what that looks like. There's another video that's separate just for molar mass that you can look up from the day 8 homework. So go ahead and check that out as well. But all right, so I have silicon. Silicon has a mass of 28.086. I have oxygen. Oxygen has a mass of 15.999. There's 2 oxygen atoms in every silicon dioxide, so I'm going to multiply that by 2. Then I'm going to add up these numbers, 28.086 plus 2 times 15.999. So I'm going to do this separately instead of opening up my calculator. I trust that you can do this addition. So I'm doing 15.086 plus 28.086 plus 15.999 times 2. And the molar mass that I get, 60.084, and the unit for molar mass is grams per mole. All right, so 60.084 grams per mole will be my conversion factor for SiO2. This is the second amazing conversion factor. So I have 2.45 moles of silicon dioxide times 1 mole of silicon dioxide is 6.084 grams. And so 6.084 times 2.45. My final answer here is 147.21 grams of silicon dioxide. All right, I hope that helped. Thank you for watching. Have a good day, everyone.